Um, good afternoon, good evening, everybody. I have been involved in science fairs and ISSN since 2015, and I'd like to share with you today some perspectives from our country and our school, how we go about doing research and what research means in our context with students, and kind of give you an idea of some of the things that we've come up with in the last 10 years to kind of make the student and teacher research process interesting, achievable, and valuable. Okay, so by way of introduction, one of the things that we've been thinking about as we do this kind of process is we've been thinking about our impact on the number of students who are engaged in physics at high school, and we're interested in the gender makeup of those students as well. So obviously at our school at QSMT in Australia, we do scientific research with the students across all STEM subjects, and actually we do non-STEM humanities research as well. My prime interest is physics, so I'm just going to focus on our physics research for the moment, our more physical sciences. So this is a worldwide trend. Australia is not particularly different from the rest of the world in this, but basically there's a worldwide trend that women and girls are not particularly engaged in the physical sciences. And this is something that has happened that is very stable over time. These kind of figures in Australia have been stable for pretty much 20 years. So in Australia, 7% of girls and 23% of boys who study physics in their final year of school. So physics is an elective in their final year of school. So you can graduate high school without studying physics. And that gives you the percentage of students who complete it in their final year of school. This works out to be basically 20% of students enrolled in physics at high school level are girls. At QSMT, I've looked at the figures for the last 10 years. We're probably slightly above national average at 10%, but for a STEM focused school, it's still quite low, the sort of participation of girls in physics. They contribute about 25% of the cohort in our schools. Looking ahead to university, so sort of as like a field idea, 20% of enrollments in physical science majors, and that includes chemistry and mathematics, they're not sort of separated, are women. Okay, and that has been very stable too for the last 20 plus years. Okay, so this is sort of something that we're kind of looking and tracking at because we want to increase the number of girls at QSMT who are studying the physical sciences, and we want to encourage them to go onto university and be involved in that kind of study as well. So in Australia, so this is a broad Australian context. Our school is a little bit different, but I'll get to that in a moment. So basically there's two groups of opportunities for student research at schools. The first group is curriculum based. So basically students in Australia study something called the Australian curriculum. And within the Australian curriculum, there are explicit curriculum opportunities or even requirements for the students to participate in science-based research. At our school, the students can do this thing called an extended essay. That's in the International Baccalaureate curriculum. There's a topic called science extension in the Australian curriculum, which involves students in grade 11 and 12. Throughout the grades 7 to 12, which is basically considered our high school in Australia, students have the opportunity to do experimental investigations as part of their science studies, and those science studies would be core kind of compulsory components that every child in Australia would do. So that's the curriculum opportunities to do scientific research. Extracurricular, we have state-based science teacher associations in Australia that promote and run science competitions, and they target students from kindergarten all the way up to year 12. There are also national and state-based science fairs that cater to students from grades 10 to 12. So that provides opportunities for students to work on projects to present at science fairs. And then there's also quite a large range of government and industry-sponsored competitions that encourage students to do research or do projects and then enter them into the competitions. Some of them have been running for many decades. Some of them sort of run for a couple of years here and there, and then the funding model changes and then are replaced with something else. And they tend to target grades 5 up to grade 12. Okay, so it's sort of upper primary school in Australia all the way through high school. Okay, so at our school, what does it look like in the curriculum? So basically our curriculum-based opportunities where grades 7 to 10 would do research is mostly teacher directed, or almost entirely teacher directed, in fact. There's limited student choice or agency. Basically, they follow a set procedure that a teacher decides in advance, and they complete they don't have any particular choice in the experiment. They might have small amount of choice in variable selection or the type of equipment they use, for example. It's usually a common task or project, so it's something an entire class or even an entire year group will complete. In terms of resourcing, there is adequate material and human resources provided so everybody can participate. And it's marked or graded using a specific criteria. So you might have noticed the ticks and crosses that I've kind of added, which is a bit of a subjective me thing that I've added, sort of identifying things that I think are positives and negatives. Okay, so curriculum-based research for the grades 7s to 10s is mainly for an assessment purpose. So resourcing and materials are really good, but in terms of being kind of an authentic or a really beneficial experience for the students, it's somewhat limited. It's not useless, but it's definitely limited. And I've just listed down some examples that we do, and these are just the physics investigations that we would do in year 7 to 10. I've got a little video, I'm not sure if you can see them. This is one of my students, and they made a slow motion video because they were investigating air resistance there. Okay, so primarily the purpose of this curriculum research is skill development, but the skills they develop are sort of lower order, if you like. So they definitely learn measurement skills. They use a different equipment and materials and things like that. They have to work in small groups, so they develop a lot of teamwork skills. They develop data collection and data processing skills. They learn to use tables and graphs and interpret graphs and tables. They have to learn how to the conventions of doing a scientific report, and they definitely learn about the idea of scientific method. Higher order skills are somewhat lacking, though. They're harder to assess, and you need a lot more time for the students to be able to develop them. And in the kind of curriculum-based activities we have, like within a day-to-day classwork, they're sort of not really achievable or manageable with large groups of students, so they're generally not attempted. Probably the one exception to the curriculum-based research, though, in our school is this thing called the extended essay. So the extended essay is a compulsory component of the International Baccalaureate program, also called IB. The students choose a topic for research within a subject area, and they just choose one. They just do one EE when they're in year 11 and 12. It's an individual research project, and instead of being in a big class, they're allocated to a mentor, and a mentor at QSMT supervises 4 students. So there's a lot more personal one-to-one interaction with the mentor, that a lot more than you would get in a classroom environment. The students have to produce a 4,000-word essay for the assessment, and the essay has a format somewhat like a science journal article. So it's not sort of the stereotypical student experimental report. It's more it's referenced and it's written in sort of essay style, so it more closely resembles a journal article. So I pulled together some data for you because one thing we've noticed is that even though we have relatively low percentage, so about 20% participation in our senior physics subjects. So when you look at the girls that are enrolled, there's about 20% of the physics cohort are women. But when they go and choose a extended essay topic, they can be as high as 50-50 girls and boys. So you'll notice in 2022, we had 50-50 students, girls, boys, who chose to do a physics extended essay. So there's something about the research environment with the mentor that seems to really suit and engage the girls in physics. um, the boys are definitely also engaged, but the girls seem to be more willing to take on a physics EE than they are physics as a subject, if that makes sense. So we have we to, because every teacher can only look after 4 students, and we have between 4 to 5 physics teachers at our school. We tend to have 16 to 20 students doing a physics EE in every year. And since 2016, we've had 177 students who have completed a physics EE. Okay, and as I said, the participation rates of girls and non-binary students is often higher than the cohort percentage. I'm afraid this year is, unfortunately, the participation rate of girls and non-binary is very low. We actually only have one girl student doing a physics EE this year, which is a bit sad. Okay, so moving on to extracurricular. So in the QSMT context, most of the most interesting student research doesn't happen in an organised class. It happens outside of formal class time, and the students and teacher mentors work during lunch breaks and after school. So teachers have to volunteer their time basically to mentor the students, and students have to give up their free time or their socialisation time with their peers in order to participate in this kind of research project. So the plus side, though, is that it's largely student directed. Students can be mentored in small groups. Resourcing, both human and material, can be quite variable. So it has to be kind of negotiated on a case by case basis. And sometimes students miss out on the opportunity because we just don't have enough either mentors or materials or both. So that is a definite cross mark. I've put that cross mark there to show that. The research that can happen in an extracurricular environment, though, is not constrained by external criteria. Like, we don't have to mark it in the conventional sense, and we don't have to give an equal opportunity to all students, so all students are getting marked to the same standard, if that makes sense. So that the lesser constraints means that you can do a lot more interesting things, and the students can do a lot more in-depth things. I think, and we're collecting data to show this, that it develops higher cognitive skills in the students, and it gives an opportunity for cultural exchange, especially if they get to travel overseas to a science fair, and also encourages participation of women and gender minorities in physics. Okay, so the next thing I was going to talk about was what I perceive are the skills that are developed in extracurricular results research. So remember before I mentioned that the skills that we were able to do in our curriculum were important and necessary fundamental skills for research and science learning, but they're kind of more processing based skills. They're definitely lower order. Okay, so if I go and have a look at the skills that we develop in extracurricular research, though, the students have to participate in an experimental design process. They're not given a recipe or a procedure by the teacher, so they have to come up with their own design for the experiment. They develop research skills, so they have to access, and in this case, I'm going to mention it in a minute, is they use scientific journals a lot, or they might access standard operating procedures of different materials or equipment to work out how they're going to design their experiment and what they expect the outcome should be. They develop advanced literacy skills. They have to be able to read at quite a high level if they're going to use scientific journals, and they have to be able to extract, interpret, and integrate that knowledge that they're acquiring through reading. They have to collaborate. So if they work in a group, they have to collaborate with their peers. They have to collaborate with their mentor. They are often given an opportunity to collaborate with somebody from university or industry who might have some expertise related to their project. And if they go to a science fair, they'll have to collaborate with the other students who are attending the fair and those sort of things as well. They have their presentation skills cross both oral, written, and visual, because usually they have to give an oral presentation and produce a report and do a poster. And as I mentioned, there's the opportunity for cultural and international engagement, which definitely being able to move in and interact in that environment means that they have to develop good interpersonal skills and empathy and, yeah, so understanding and really good listening. So I'll just show you what our data looks like for student participation in extracurricular research. So we've been participating in national and international science fairs since 2015, and this data is from what I've kind of called the physics subsection of the projects that we've done. We've done 50 projects that could be classified as physics broadly. We have done many more. So we have done projects that would fall into like chemistry, biology, biomed, and mathematics and computer science as well. So we've done more than 50 projects since 2015, but these 50 projects are in physics, and these 50 projects were all presented at either a national or an international science fair. And as you can see from the graph, the participation by girls in these extracurriculum research projects in physics is very high. Okay, in many cases it exceeds the percentage participation of the boys. Okay, so once again, there's something about this style of extracurriculum research, the mentoring and the sort of opportunity to work at a high level and work more deeply that is really appealing to girls and non-binary students, and they have much more higher representation in these projects than they do in a general physics class. Okay, so the next thing I want to talk to you about was I wanted to talk to you about sort of the hack that we use in physics that allows us to facilitate this kind of extracurricular research without basically going mad. Okay, so student choice in research is fantastic, and I think the ability for students to choose their research is one of the driving factors of the higher order cognitive skill development and the increased participation of girls and non-binary students in physics research. I think both of those factors really motivate those students to be involved in those kind of projects and to do that kind of work. So the problem is, while student choice is fantastic, it presents a lot of dangers in terms of then facilitating that research. So one of the main dangers is that students will choose something and you just do not have the material resources to be able to do it at school. So in QSMT, ever since COVID, we pretty much don't do any of this research anywhere else except in our school lab. Prior to COVID, we used to have the opportunity to occasionally, not super frequently, go to universities and use university labs or even use industry labs. Over COVID, so from 2020 to 2023, our access was completely restricted because of the way that businesses and schools and everything were locked down in Australia during that time. And since COVID, there's been a lot of extra bureaucratic requirements that have really limited our abilities to get students into those other labs. So we need to be able to do these amazing things that students choose and want to do in the lab. And that can be a real problem if we don't have the materials or the resources, either because the resources are expensive or dangerous or just in short supply or sort of bespoke made kind of resources. So that is a problem. The other problem is risk management. Like there's some things that we can't actually do in a science lab that you would be able to do in a university or an industry lab. So that can really restrict what it is that the students can choose. Mentor knowledge and experience. So we're asking mentors for this research to give up their time, and we need them to have the confidence and the willingness to help the students in their project. But mentors are unlikely to volunteer if the projects are outside of their knowledge and experience. They don't feel comfortable or confident in doing things that they have never done before, or they haven't seen done, or they don't know will work. And that is another major problem with student choice. Sometimes they choose stuff that won't work or it will work, but it will take, 40 hours of work in a lab to make it work. So that is not achievable in terms of the time resources of the people involved or the material resources of the school. So our solution to these problems was to use journals. So, and this is why I'm mainly talking to this about physics, because it mainly happens in physics. So you can see a photograph there of two of our year 11 students, and they're accessing journals on a magazine rack that is permanently in our physics lab. And the journals that we have a variety of journals, but the ones that are most useful for physics research are the Physics Teacher and the American Journal of Physics. We also frequently use journal articles from Physics Education. So the Physics Teacher and Physics Education are completely accessible for students in Australia from grade 10 and above. They might not understand every word in them, but they can read the introduction, they can see results and graphs, they can read the conclusions, and they can get the basic idea of what is happening within the experiment or the study that has been reported. American Journal of Physics is usually the second stop. So you find something that interests you in the physics teacher, and then you look for further, more detailed, more mathematical treatment in the American Journal of Physics. There are some great things in the American Journal of Physics, but the American Journal of Physics is primarily aimed at an academic university audience. So sometimes it is a little bit too difficult for a student and needs help from the mentor to interpret, if you like. The physics teacher and physics education are primarily written for physics teachers at secondary schools and undergraduate university physics teachers. So they're quite accessible to high achieving physics students. So I'll just give you some examples of what we do. So this is an example of a student who was So basically what we do is we say, oh, you want to do a physics research project, go and have a look at the magazines. So they go over and have a look at the magazine rack, and then they find something that interests them and they pull it out, and then the mentor will have a discussion with them. We'll talk about whether that sort of thing's been done before and how maybe we should design something that might be a bit different, or it might answer a slightly different question that's in the journal. This is an example. So on the left is a page from the journal article. This one happens to come from the American Journal of Physics. And in this journal article, they described this damping of motion from a drinking straw. So this is a observation that you can make with any drinking straw and a cup of drink. If you cap the top of the straw with your finger, you can suck up a column of fluid in the straw. And if you release it, it will bounce and it will move down the straw and bounce off the surface, and it will oscillate and sort of decay in this damped motion. So this student liked the idea of that and wanted to adapt this experiment to look at viscosity of fluids. So the photograph on the right shows you the experimental setup. So the experimental setup was explained in the article, so the student was able to copy it and experiment with it and make a few design changes of their own. But this was a very simple one. This experiment was actually done during COVID, so it's actually done in the student's house because it was like kind of safe and the materials used were not dangerous or difficult to achieve. And then they used a slow motion video to record the movement of the column of fluid, and then they analysed it and used the damping coefficient to calculate the viscosity of the fluid. So that's one example. Here's another example. This comes from the physics teacher this time. So this was a journal article that described how you could sort of simulate Rosalind Franklin's X-ray diffraction experiment to find the double helix shape of the DNA molecule by doing a diffraction experiment with light and a pen spring, so the spring that's found inside a retractable ballpoint pen. So this student once again looked at the journal article, thought, oh, that looks pretty cool. I wonder if I could do that myself. And they decided that they were going to see if they could measure the thickness of the wire in the spring, the separation of the coils, and this thing called the pitch, which is kind of the angle of the spiral as it moves up the spring. So they set up the experiment as it was described. So you can see there's an outline of the experimental setup there, and there's some sample data. So they got a spring, and they set this up. This was slightly tricky to set up because we needed to have quite a large distance to the screen in order to see the details in the diffraction pattern. So that was a bit challenging, but we managed to work it out. Then they photographed the diffraction pattern, and then they used this thing called a line profile in a freeware software called Tracker. It's a video analysis tool that is developed by physics researchers, and students can make use of that. And then they were able to measure the distance between the fringes and answer the questions they had about the dimensions of the spring. This is another one. I know some of you might have seen this before because I have actually spoken about this project at a ISSF event before. This is a oscillating or a seesaw candle where you burn the candle at both ends and the candle oscillates. There's quite a few journal articles in both the physics teacher and the American Journal of Physics about oscillating candles. They seem to be an endless source of interest to physicists. So this student was inspired by an article that they saw in American Journal of Physics and the physics teacher, and they videoed the experiment. This is a sample of their data, so you can see there's a lot going on in this experiment. It's a very complex system to model. So the idea of modeling is a very important skill in quite a lot of these projects. This is another one. You may be familiar with the popsicle stick cobra, where you lattice popsicle sticks and then you release them, and then a wave basically is generated in them as they relax because they're under tension, and it moves down. It's kind of like a weird popsicle domino effect in a way. So the physics involved in this is very complicated, but the student was inspired to attempt to model a somewhat simpler aspect of it and made use of high frame rate videos to measure the velocity of the wave front as it moves through the popsicle cobra. And you can see some of his data down there too. Actually, the original inspiration for this was at the Japan Super Science Fair. One of the Tokyo schools had a research project on it, and I photographed it and showed it to this student. And then he went searching through the journals and found some um, journal articles about it. Okay, this is the last one I'll show you as an example. In these journals, especially in the physics teacher, there are experiments described that collect data, but there's also a lot of simulations and demonstrations that they suggest that you show in class to kind of help the students understand more complex or difficult ideas. And this was a description of a simulation for gravitational waves being produced by orbital binaries. And it came out pretty shortly after the LIGO results for gravitational wave detection started circulating in the journals and in the physics community and making people very excited. So this student took this simulation idea and took the mathematical model that relates frequency to rotation of these orbiting binaries, and actually designed an experiment to make measurements. So he kind of went well and truly beyond the conceptual simulation and sort of turned it into a numerical quantitative experiment. So that happens quite a lot too. There's a lot of like, oh, hey, look at this cool thing in the physics teacher magazine. But a lot of those cool things can be turned into sort of demonstrations and simulations into actual experiments where you collect data. So to wrap up, journals in student research, it gives the students a starting point to consider a variety of quality projects. It really cuts down the sort of aimless Googling of ideas, and it stops the constant repetition of those very, very overfamiliar, been done a million times before kind of science fair projects that students tend to come across when they are trying to come up with an idea, but they don't really know where to start looking. Okay, it gives them a much more practical starting point with a lot of quality research and quality projects. The projects in these journals are almost exclusively achievable in a school setting, particularly the projects described in the Physics Teacher Journal and Physics Education Journal. That because those journals are aimed at physics teachers, they usually are done with low cost school lab based level equipment, or they'll make suggestions for substitutions so you can do them at school. Okay, they provide lists of sample materials, they show basic setup, and they often provide sample data. So if you've never done these experiments before as a mentor, you kind of know what you're going to get before the student starts. So if the student's getting something totally different, you've got a starting point for troubleshooting rather than being completely lost in a topic that you've never done before and you don't know much about. The students have to learn how to use academic databases and journals to find the information. I really love it when the students suddenly realise that they can use the reference list from one article to find relevant other journal articles. So, and it becomes a bit of a sort of a follow the leader kind of idea where they use one journal article to find the next, to find the next, to find the next. And it's really useful, I think, because students see that science research builds on the work of others. It's almost impossible for students at high school level in physics to do something original. And I don't think that's necessarily a bad thing, because most of science, even in university, is a small incremental building upon something that someone's already done before. And if students can see that in high school, it can make a big difference to their perspective and how they can achieve something in research in tertiary studies. So that's basically everything I was going to say today. I don't know whether you want to do questions now or maybe at the end. So thank you very much for listening to me, and I hope it has been of interest and of use to you.